There are four types of ionic compounds. And as you can see over here, the first type is the ionic compound that is going to be made of a representative metal. Remember, metals that are in group 1, 2, or 13, or 1A, 2A, and 3A, and monoatomic ions. These ionic compounds, they are also known as binary salts. See? In addition, we have another type of ionic compound that is made of transition metal and monoatomic ions. Every time that you have an ionic compound that is made of a monoatomic ion, these ionic compounds, they are known as binary salt. In what binary? You know that binary means two, because you're going to have only two elements involved in that compound. You're going to have the metal, they could be representative or transition, and then you're going to have only one non-metal involved in that compound. Now, we have another type, which is the ionic compound that is made of a representative metal and a polyatomic ion. Okay, and that type of ionic compound is also known as tertiary salt. Remember that when you have a metal combined with a non-metal, the metal is going to lose the electron while the non-metal is going to be accepting that electron. That type of bonding is called ionic bonding, and the compounds that are formed, they are called ionic or salts. That's what we're talking here about, binary and tertiary salts. Now, when you have ionic compounds made of representative or transition metal and polyatomic ions, since you're going to have more than one non-metal involved in that compound, they are also known as tertiary salts. And we're going to start with the first group. The first group, as you can see over here, is the group that is going to be made of a representative metal and a monatomic ion. How are you going to name this ionic compound? Simple. Okay, you're going to write the name of the metal. You don't have to change anything. And then you are going to write the name of the non-metal, but you're going to drop the ending and you're going to add IDE. You have your first sample over here. Potassium is in group 1, and then you have a non-metal, only one non-metal, meaning that you have a monatomic ion. How are you going to name that compound? First, the name of the metal. Potassium. And remember that you're always going to have a periodic table. So you're not going to have any problem looking for the name of the element. Second step, you're going to look at the non-metal. The O is for oxygen. You're going to drop the ending, and then you're going to add IDE. Oxide. See that? No oxygenide, oxide. And that's how you're going to name ionic compounds made of representative metals and monatomic ions. Example number 2. Okay, if you look at your formula, B, beryllium, is a representative metal because it's in group 2. And when you look after beryllium, you have only one non-metal, meaning that you have a monoatomic ion. How are you going to name this? The name of the metal, which is beryllium. And then you have nitrogen. But remember that you have to drop the ending. And you're going to add IDE. So the name of this ionic compound is beryllium nitride. Okay? Let me see if I can find another example. And this first type of ionic compound are the simplest one, because you don't have to worry about oxidation number, and you don't have to worry about the name of the polyatomic ion. So one more time, you're going to analyze. See, calcium is in group 2, and after calcium you have only one nonmetal. So I know that I cannot change the name of my cation or positive ion, calcium, chlorine or chlorine, I don't know how you pronounce that, but chlorine becomes chloride. Chloride. Second type of ionic compound are the ionic compounds that are made of representative metals. And when we're talking about representative metals, you know that there are the metals that are located in group 1, 2, or 13. And they are classified as representative metals because they follow the general trends. We were discussing that before when we were analyzing the periodic trends on the periodic table. You know, the representative metals, they have a fixed oxidation number. Only one oxidation number. That's why you don't have to specify the oxidation number that the representative metal is showing, because one of the characteristics of that representative metal is that it's going to have only one. So when you have an ionic compound made of a representative metal and a polyatomic ion, how are you going to name that ionic compound? The answer is easy. And you have that over here. See, the general formula or the general format just to write the name of ionic compounds made of representative metals and polyatomic ion is to write the name of the metal followed by the name of the polyatomic ion. Now, what is the most difficult part? That you don't know the name of the polyatomic ions. That's the most difficult part. Now, do you have to memorize them? The answer is no. Here in high school, I'm not gonna make you. I should, but I'm not gonna make you memorize like a list of common polyatomic ions. You will do that when you go to college. The teachers out there, they will give you a list that you will have to memorize. Remember, since they are ions, you have a chemical formula for the polyatomic ions, and also they have a charge, an oxidation number. That's super important. I don't know if you have been looking at the videos that I'm posting, but there's an application from Carolina Supply that is helping you memorizing the name of the polyatomic ions. Okay, I recommend that application. It costs, I think, $1.99, but it's gonna help you with your fluency when you have to memorize your polyatomic ions. So we're going to start here with the first example. Example number 1. Remember that I'm talking about metals that are in group 1, 2, or 13, or 1A, 2A, and 3A. Okay, and I know that the formula is big and looks scary, but you'll see that it's easy to name. So over here, that's just your first analysis. Okay, when you have your chemical formula in front of you, you're gonna look at the first element. If the first element is a metal, right away, you know that you have an ionic compound. Okay, a metal. Is this metal in group 1, 2, or 13? The answer is yes, because if you look at the periodic table, aluminum is in group 13 or 3A. Now, when you look after the metal, do I have one or more than one non-metal? In this case, you have more than one. Oh my goodness, this is a polyatomic ion, so I have to look at the list. So I know, see, that the metal is not going to change the name. So aluminum and And then I'm gonna look at the polyatomic ion SO4, and I'm gonna look over here, sulfate. And you're done. You're done naming your ionic compound. So one more time, name of the metal, followed by the name of the polyatomic ion. And since you're gonna have the table with the list of the common polyatomic ions, I don't think that you're gonna have any difficulties with this. Example 2. Super important. Don't get scared by the subscripts that you have over there. Okay, if you don't know where the 2 and the 3 are coming from, just watch the videos addressing writing chemical formula for ionic compounds. You'll see where the numbers are coming from. These 2 numbers, they're not going to affect the name over here of the compound. Okay, so example number 2. My metal variant is in group 2, so it's a representative metal. And after my metals, I have more than one non-metal, so I have a polyatomic ion. So I'm going to proceed accordingly. So the first step is to write the name of the metal variant. Remember, the cation never change the name. Cation never change its name. Now, NO2, let me see if I have that over here. NO2, nitrite. 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 See that? Because you were getting that from your list of polyatomic ions. Sulfate from here, nitrate. See, those are the common ones that we're going to use in our chemistry class. Okay. Last example. Sample 3. Let me see. I'm going to use Cl. Okay, one more time. Lithium, as you look in the periodic table, is in group 1, so it's a representative metal. Do I have to change the name? I'm going to keep the same name. So lithium. Lithium. Now I'm going to analyze. After the metal, do I have more than one non-metal? The answer is yes. Okay, so I have chlorine over here together with oxygen. Okay, by the way, you know that this is called an oxy. All of them, see, are called oxy anions. Okay, so I'm gonna look on my table for this polyatomic ion or hypochlorite. Hypochlorite. Okay, and you're done. See, this is the way that you name ionic compounds that are made of representative metals and polyatomic ions. Now, what happened with the third group of ionic compounds? The third group of ionic compounds is also known as binary salt because you have only one non-metal involved, see, made of monatomic ions. But you have transition metals as part of the compound. What happened with the transition metals? Many of the transition metals, with some exceptions, have more than one oxidation number. So when you are naming them, you have to state the oxidation number that the metal is using in the compound, reading in Roman numeral, and between parentheses between the name of the metal and the name of the non-metal. How are you going to do that? Let me see. Let's going to start with example number 1. Example 1. Let's say that you have this formula. So your first step is just to analyze the metal. Okay, so this is the symbol for iron. But iron is a transition metal. A transition metal that has different oxidation numbers. Okay, so we have different approach to find the oxidation number, but right now we are going to concentrate on naming, and the last thing that we're going to do is just to find the concentration number, the oxidation number. Now you know that iron is a transition metal, so you're going to start naming your compound. Iron. Since you know that iron is a transition metal, you're going to open in parentheses, you're going to leave that in blank in there, and then you're going to look at the non-metal. So you have only one over there is a monatomic ion, the ending in IDE. Now, once that you have the name of the metal and the non-metal with the ending IDE, we're going to concentrate on finding the oxidation number of the transition metal. And I have three approach. We're going to start with the first one. The first one is trial and error. Okay, so I'm going to give you, together with the list of polydimic ion, I'm going to give you a list with the possible oxidation number of the different transition metal. If you look at the list, iron has or can show two oxidation number, 2 positive, 3 positive. Okay, so once that you have the oxidation number, you're going to write the element symbols with the oxidation number. Now you're going to look at the compound that you have. Iron combined with chlorine. Chlorine is in group 17. 17 oxidation number is -1. It's a halogen, 17 oxidation number -1. And now you're gonna dance, baby, dance. And by dancing, I mean that you're gonna switch the oxidation number without the sign in front. Because remember that when you're writing chemical formula, you are going from the oxidation number, which is the number of electrons that is gained or lost during a bonding, to the number of atoms. Can you have a number of atoms that is equal to -1? The answer is no. We are gonna do the same over here. So we are gonna dance, baby, dance. And as you can see, that 3 that you have on the chlorine is the oxidation number of the iron. Now, this is not the formula that you have there. The formula that you have in your component is that one. So what is the oxidation number that iron was using? 3. So you're going to put the 3 over here. And that's the first approach. We have another approach that works for every single problem, which is the mathematical approach. Okay? So it's up to you. I'm not going to force you to use any specific approach. You're going to pick one and you are going to work out your problems. So the mathematical approach is based on the fact that when atoms combined, they are combining because they want to reach chemical stability, and at the same time the net charge of a compound is equal to 0. Okay, so if you look over here below the iron, how many atoms of iron are involved? You have 1. What is iron oxidation number? You don't know that. That's why you're gonna put an X, or you can put a Y, or you can put a V, or you can put whatever letter, because remember the variable is representing a value that you don't know. So when you add the number of atoms multiplied by the oxidation number of the element plus, of the metal, plus the number of atoms of chlorine that are involved multiplied by the oxidation number, which by now you should know, because you know that chlorine, fluorine, bromine, iodine, they are halogen group 17 or group 7A. They need one more electron to reach chemical stability. The oxidation number is equal to -1. When you add the 2 multiplication, that has to be equal to 0, because when they combine, they form a neutral compound and more stable. So you have to solve that. X minus 3 is equal to 0. Solving for x, you cancel that. So the oxidation number of iron, positive 3. And this one works for every one, every problem. And the other one, okay, sometimes works, sometimes doesn't, undo it. Why undo it? Because this is your formula. Okay, so you know that since you have to dance, baby, dance, when you are writing formula, you're gonna undo that. So the 3 that goes here, over here, you don't have anything, that means that you have a 1, it goes there. So if from there you can get the 3, which is the oxidation number, that is iron showing in that compound. Example 2. Example 2. My first step is to analyze lead. Okay, so I'm gonna write that down. Lead is a transition metal with different oxidation number. So I'm gonna open that, the parentheses, to find the oxidation number of lead. A monoatomic ion, so ending in IDE. And now I'm going to concentrate all my energy to find the oxidation number of lead. You know what you're thinking? Miss Ramos, this is so easy. This is lead to oxide. Wrong. That's why I don't like the undo it approach. Why? Because in that case, you're going to get the number that goes here wrong. So I'm going to use the mathematical one. Or I can use the trial and error. Okay, so let me use the trial and error and then the mathematical one. So I'm going to start with the trial and error. Error. If you look on the list with possible oxidation number, you know that lead can show 2 oxidation number, positive 2, and lead can use positive 4. Okay, that's your first step. Just to write the element symbol with the possible oxidation number. Now, what happens when you have a transition metal that have 5 oxidation number? Is it like practical to use the trial and error? So I recommend that when you're naming an ionic compound made of a transition metal, if that transition metal, when you look at your list, has more than 4 oxidation number, just use the mathematical approach. But in this case, in lead has only 2. Okay, only 2. I'm going to use the trial and error. Then I'm going to continue. Because lead is in a compound with oxygen. You know that oxygen is in group 16 or 6A. 6 electrons on the last level of energy, is a non-metal, so it's going to accept 2 electrons, oxidation number -2. And once that you have the symbols and the oxidation number, you know what you have to do. You dance, baby. You dance. So, by dance, remember that I mean just to switch the oxidation number. In this case, what's going to happen? Since they are the same, they're going to cancel. So the formula will be the 1. In this case, on the second case that you have over here, after you do the dancing, you have PB2 or 4. 2 and 4, they are multiples. Since you know the elements, they combine in the smallest ratio, you have to simplify, so you have to divide by 2. And this is your formula. So once that you finish with your trial and error and your dancing and your simplification, you're going to analyze. Is this the formula that you have? No, that's not the formula that you have. What is the formula that you have? That over here. What was the oxidation number that lead was using? 4. So you're going to write over here 4 using Roman numerals. Now, let's say that you want to use the mathematical one. mathematical approach. How many atoms of lead are involved? 1. Multiply by the oxidation number. See that I'm using another letter. It doesn't matter. Multiply by the oxidation number of lead that I don't know. So I'm going to add that to the number of atoms of oxygen that are involved. That is going to multiply the oxidation number of oxygen. So number of atoms of lead that are involved in the compound, multiplied by the oxidation number, a number that I don't know, plus the number of atoms of oxygen that are involved in the compound, multiplied by the oxidation number of oxygen. So I'm going to solve this. Minus 4 equal to 0. Inverse operation. A is going to be equal to positive 4. And that's the number that you're going to write between parentheses in your in the name of your compound. Okay, another quick example. Let me see another example. Not that complicated. Okay, this is my example number 3. Okay, Ms. Ramos, one more time. I'm going to look at the first symbol. If the first symbol is a metal, right away I can conclude that I'm in front of an ionic compound. Okay, but a silver. When you look on the periodic table, silver is a transition metal. Silver is a transition metal located in group 11, the group that are, in the center of the periodic table. So I'm going to start writing the name, okay, because the cation never changed the name. So silver. And I'm going to open a parenthesis over there because according to you, Ms. Ramos, every time that you have a transition metal and the transition metal has more than one oxidation number, I have to put that over there in my name. Okay, so now I'm going to analyze monopoly. I have only one, so it's mono. Sulfur become sulfite. Okay, Ms. Ramos, now we're going to concentrate on finding the oxidation number of silver. But you look at the table, and in the table it says that silver has only one oxidation number. One oxidation number, which is plus 1. Do you have to write that over there? The answer is no. So if you have a transition metal, and when you look at the list, that transition metal can only show one oxidation number, you don't have to write the oxidation number between parentheses. It's only when you have transition metals that have more than one oxidation number. The majority of the transition metal, they have more than one oxidation number. But you have a couple of them that they have only one. I think that zinc is another one, and mercury, but I'm not sure about that. Okay, you don't have to memorize that. I'm gonna give you a table the day of the test with the list of the common polyatomic ion plus a list of the possible oxidation number for transition metals. This is the last group and the more complicated because you have to look at the name of the polyatomic ion, but at the same time also you have to find the oxidation number of the transition metal. So how are you gonna do that? How are you gonna make ionic compounds made of transition metal and polyatomic ions? You're gonna combine all the things that you have learned. First, remember the metal is the cation, doesn't change the name. We're gonna continue with the same strategy. Okay, so over here when you analyze, you have cobalt. But cobalt is in group 9, so it's a transition metal. We need to find the oxidation number, but we're not going to do that now. We're going to open a parenthesis, and now we're going to concentrate on the second part. Look at the second part. I have two. Okay, by the way, this O that you see over there is an uppercase O. PO3. I have more than one non-metal. It's a polyatomic ion. What is the name of this polyatomic ion? PO3, oxidation number -3, phosphite. Okay, so I'm gonna write over here phosphite with T. Okay, remember it's a polyatomic ion. Now cobalt phosphite. Are you done? The answer is no, because you have to find the oxidation number. Okay, cobalt. I think the cobalt has like 4 oxidation numbers. Since cobalt has so many oxidation numbers, and I'm going to use the trial and error approach. I'm going to use the mathematical approach. Mathematical. Why? Because I'm going to be able to find the oxidation number faster. Okay, mathematical approach. How many atoms of cobalt do I have there? 1. Oxidation number of cobalt, I don't know that, so I'm going to multiply by B, which is going to represent the oxidation number of cobalt. Plus, and now you have to analyze, because this is the part that you get confused. How many groups of the polyatomic ion do I have? If remember that the formula is PO3 -3, so you have only one group. What is the oxidation number of that group? -3, and when you add the multiplication of the number of atoms by the oxidation number, that has to be equal to 0 because the compound is neutral. You solve this opposite operation or the inverse operation, add it inverse, oxidation number of cobalt is +3, which makes sense because remember that you're always looking for the oxidation number of a metal. Can a metal have an oxidation number that is negative? That's one of the things that you can use for self-checking. Let's say that you're solving your mathematical equation and you get a negative number. Is that possible? That means that you make a mistake. So I'm going to write over here my 3 Roman numbers. We're going to continue over here with example number 2. 2. Example 2. Let me see. What do I have in here? A ver. Miramos. That formula, so big. I know what is your reaction, that every time that you see more than 2 elements on a formula, you get scared. Okay, but you're going to follow my step. First, you're going to analyze the first element that is involved. And I want you to notice that the compounds that I'm putting over here, I'm making them up. I don't know if they exist in real life. I'm just making them up. Okay, so I'm going to look at the first one. V. Okay. Vanadium is a transition metal. So this is an ionic compound. And if you use that approach, always you're going to be able to name any compound. Remember that this is just the beginning. We are learning about ionic, but you know that we have covalent compounds. So you need to know how, or you need to find a way to differentiate them. But if you see a metal, the first one is a metal, that's an ionic compound. Vanadium. You're going to write that over here. Vanadium. Okay, but vanadium is a transition metal. A transition metal that when I look at my table have different oxidation numbers. So I'm going to open a parenthesis. After that, I'm going to analyze what comes after the metal. Here I have 2 non-metal, SO3. What is the name of the polyatomic ion? Sulfite. Now we're going to concentrate on the oxidation number. And this one is so easy because if you look on your table, SO3 -2, oxidation number of sulfite is -2. If that -2, you know that is coming from the That 2 that you have over here is coming from the sulfide. So this 5 over here is coming from where? From the vanadium. This is one of the cases in which you can use the undoing approach because the oxidation numbers, they are not multiple. So this is the name of this ionic compound, vanadium 5 sulfide. When the oxidation number, see over here, didn't work because they were the same. Okay, were the same. If you have 6 and 3, you have 4 and 2, if you have 2 and 2 or 3 and 3, see if they are the same or they are multiple, my advice, use the mathematical approach because you're going to be able to find that easy. But in this case, when they are not multiple, you have a 2 and a 3, you have a 2 and you have a 5, or you have, see, a 3 and a 2, you can use the undoing approach and then you're going to find that like super quick. Okay, so another one, this last one that we are going to analyze here. Sample number 3. Well, let me see. No, I used that one already. Super easy to use the same approach. We're going to use the same approach. The first one, copper. Copper, I'm going to open that between parentheses. Polyatomic gallium hydroxide. Hydroxide, when you use that, the table of polyatomic gallium oxidation number is -1. So the 1 over here comes from the hydroxide. So this 2 is coming from where? And if you look at the list, with the common oxidation number of transition metal, you know that copper can show +1 and +2 oxidation number. In this case, is using 2, copper 2 hydroxide.